welcome to the third edition of our summer lecture series for 2003. We're glad you could join us again today. I'm Ron Kolb from the Communications Department, welcoming you here. I was talking to Cheryl, my colleague here, who said that anytime she sees a talk with allure in the title, she's there. She's going to listen to it. So we know that it's going to be an alluring talk. And without further ado, I'd like to ask Dan Croats from the Communications Department to come up and introduce our speaker. Dan?
Thank you. Today's speaker is Stephen Visco, and he's an internationally recognized expert in solid-state electrochemistry. He's a principal investigator in Berkeley Lab's Material Sciences Division, where his research is focused on fuel cells, gas separation, and ceramic membranes. He received his bachelor's degree in chemistry from the University of Massachusetts and a PhD in physical chemistry from Brown University in 1982. He joined Berkeley Lab in 1984 to work on high-energy density batteries and related electrochemical systems. In addition, in 1990, Stephen and fellow Berkeley Lab researcher Lucas de Jong founded Polyplus Battery Company. Located in Berkeley, the company is devoted to advancing the state of battery technology. Stephen serves as the company's director of research. He has also published extensively on batteries and fuel cells and currently holds 25 U.S. patents in those areas. His research is funded by the U.S. Department of Energy, the Defense Advanced Research Projects Agency, and several U.S. and foreign companies. His talk today will highlight his group's work developing solid oxide fuel cells. Stephen?
Thanks, Dan. Thanks for the introduction. I'm going to talk to you today about fuel cell technology. The work we do at the Lawrence Berkeley Lab in the Material Sciences Division is focused primarily on solid oxide fuel cell technology, but fuel cells are really in the news quite a bit right now, and that's because of the possibilities of putting fuel cells into cars and distributed power generation, and there's just, as well as announcements about fuel cells for portable power for laptops, and so really there's a lot of attention being given to fuel cells, but these are not all the same type of fuel cells. So I'm actually going to talk about the different types of fuel cells, and then at the end of the talk I'll focus on what we're doing here at the lab. And so then I'll start with really just to refresh those who are not familiar with fuel cells, what fuel cells really are and why we want to use them. I mean, what's the attraction to fuel cells? And the market size. I mean, how big is the market? And it's the market that drives all the research, because that's where the possibilities are. Fuel cell cars, again, this is where we hear a lot. I mean, obviously that's an enormous market if it's real. And fuel cells for stationary power. And then, of course, where do you buy them? Are they real? They're actually affordable. I'll talk a bit about that. Then I'll talk about what we're doing in-house here at LBL. Thin film ceramic fuel cells, that's ultimately what we do, and then what we call metal supported cells, which we think is the future of SOFC, and some coming attractions. Okay. So principle of fuel cell operation. Really, a fuel cell converts chemical energy to electrical energy. And you can calculate the voltage of a fuel cell based on the thermodynamic driving force for that chemical reaction. And so the basis of any fuel cell, and actually any battery, is some kind of an ionically conductive membrane that separates the two electrodes. And so that membrane can be solid, liquid, or polymeric. The large attention being paid to fuel cells right now in the press is largely focused on polymeric or PEM fuel cells, which are supposedly going to go into cars. We work on solid fuel cells, high temperature fuel cells here. So these membranes will conduct either oxygen or hydronium. The PEM works on hydronium ions, and the solid oxide fuel cell works on actually oxide ion migration. And of course you need electrodes. So the membrane separates the electrochemical reactions, and the electrodes do the charge transfer reaction. And so that's the fundamental basis of any battery or fuel cell. Now you need a fuel, and where does that come from? Well, in fact, you can use a renewable. All right? You can start with corn, and from corn you can ferment that, and you can get methanol and ethanol. And methanol and ethanol have a very attractive property, which is that they're liquid fuels. And so people think about using methanol-powered fuel cells, for instance, to recharge the battery in the laptop or power a cell phone. Okay, but really from methanol and ethanol, ultimately you get hydrogen, and then there's a whole issue of the hydrogen economy, which I'll address somewhat, and some of the problems with the hydrogen economy, and methane. Now, methane, methane is very attractive for stationary power because we have a very extensive infrastructure for methane. It's all through the US and many countries. The methane comes right to your house. So if you had a fuel cell that run on methane, you could generate your own power. And in fact, that will probably be done. The oxidant in the fuel cell is simply air. It's there. And of course, it doesn't add any weight, so you've got the air for free. So you need these elements then. And of course, you need electronic path, which then will light a light bulb, turn your laptop on and do what it has to do, run your microwave oven. All right. Portable power. There are actually fuel cells now under development by a variety of companies. This is actually a German company. They have something called a smart fuel cell. This is a methanol-powered fuel cell. And here's a methanol-powered fuel cell running like a PDA or a cell phone. And of course, we know that President Bush has kind of endorsed this kind of technology. Whether or not it's real or not is another question, so we have to look at that. Okay, how new is this stuff? It's not that new, okay? So this is a phosphoric acid fuel cell, and they were actually in commercial production until just about a year ago. This is actually, was already pretty advanced in 1965, and I was not part of that effort. And here's a Nafion membrane. This is the basis of all PEM technology. So fuel cells for cars, this is it. In the early 1960s also, and this work started at General Electric. And in fact, you can buy now a PEM fuel cell, a generator. And you can see it right here. This is produced by Ballard. Interestingly, this is a 1 kilowatt PEM fuel cell. You cannot buy it yourself. They're only selling it to essentially companies and industrial users, corporations. And the reason is because this is still, I think, a very iffy thing because, in fact, if you look at the price, it's $7,000 for a kilowatt. And it runs on hydrogen. So, I mean, none of us have hydrogen piped into our houses. So this is kind of still, I'd say, a demo, something that you install to show that fuel cells can actually do things. All right. Why fuel cells? This is really why we're looking at fuel cells. If you look at a combustion engine, the efficiencies are not, they're not bad, but they're not great either. And in fact, when you move toward diesels, you get higher efficiencies. And in fact, going further, you look at, for power generation, it's generally gas and steam turbine. And those scale up to the 100 megawatt size. So this is really also the scaling of these things as you look at distributed or actually centralized power generation. And fuel cells have this very large advantage. One is that the efficiency can be much higher, and they scale well down to very small sizes, and they still are efficient devices. Now, the other thing about fuel cells that's very attractive is there's no moving parts, and maybe a blower in some cases, but essentially no moving parts. And there's no NOx and no SOx because there's no combustion in a fuel cell. So hopefully there's also minimal maintenance. Now, these things are very attractive. Now, the other issue, though, here is that this technology is entrenched, and it's got a very large market, and it's relatively inexpensive relative to what this stuff costs now. So for this to be real, it has to be more than just non-polluting. It has to be affordable, and that is the big issue. So here's a car. $6,000, methanol powered. But as you'll see, it's pretty small. And that's $6,000. So there's definitely an issue here with things like methanol-powered fuel cells, and I'll tell you why these things are so expensive. So fuel cell cars, right? There's a lot of talk about fuel cell cars. This is actually a concept car revealed by Toyota on January 2003, and this is a fuel cell hybrid concept. Ford has got this. This is actually a hydrogen-powered internal combustion engine, which is also very non-polluting. And leave it to Ford, of course, to introduce a monster car, functioning on hydrogen. But it takes a lot of kilowatts to power a car, and you pay a lot for kilowatts when you're buying fuel cells. So let's see how that translates. Here's a Toyota Camry. It's about 157 horsepower, which is 100 kilowatts. If you look at just the cost of platinum in state-of-the-art PEM fuel cells, it's about $60 a kilowatt. That's just the platinum. So that means that 110 kilowatts is $6,600 just for the platinum. And this is about as low as anybody thinks they can go in terms of the amount of platinum required to do this job. I mean, to move these cars and get the kind of output that you need. That's not system cost. That's not the membranes. It's not the stack and all the other things. And in fact, it's the system cost is much, much higher. In fact, I'll show you what that looks like. Okay. There's also talk about the hydrogen economy. Now, the reason the hydrogen economy is necessary for these cars is that they don't run on gasoline. You can't put gasoline into one of those cars because, in fact, you really have to convert the gasoline to hydrogen. And that's a very complex and also costly problem. And so the push then is, okay, if we're going to have these hydrogen fuel cells in cars, then we need a hydrogen economy so you can get the fuel to put in the car. And in fact, there's a lot of money being spent on this, and there's actually development of infrastructure for hydrogen. And here you see, this is actually, in Las Vegas, a filling station, okay? And it can dispense hydrogen or compressed natural gas and hydrogen to fuel cell cars. And there are going to be more of these going in the US. Now, what about the hydrogen economy? I mean, you can't talk about hydrogen fuel cell cars with at least touching, base on the hydrogen economy itself, which is going to see a lot of funding. But I think a lot of people have started to voice concern about this because some very basic fundamental problems, I mean, just looking at the thermodynamics of hydrogen, the hydrogen economy itself. Alf Bossel, who runs the European Solid Oxide Fuel Cell Forum, gave a talk last year, and so these are, in fact, his slides. And it's a very simple calculation. If you look at the heating value per liter for different fuel options, okay, and these fuel options then could go into fuel cell cars, here's the problem. Here's hydrogen at 200 bars. Methane is much higher heating value, much higher energy content. But you look at gasoline, which is liquid, is even better. And this is liquid without any, this is just a liquid at room pressure, at ambient pressure. Liquid propane, liquid methanol, but hydrogen is way, way down there. There's very little energy content per liter. It's a huge problem. And the problems get worse. If you try to compress it, in fact, even liquefy it, this is the energy required to do that. Well, for methane, the energy required to get up to 800 bars is not that bad, but helium and hydrogen, very difficult to compress. It's going to be very expensive to do this. So if you're going to carry around this compressed fuel, if you want to even call it a fuel, it's really a chemical. It's hard to call it a fuel because of these problems. So let's go a little further. And this is actually, I think, maybe the most interesting slide. This is the energy consumption just to move that fuel. So if you look at gasoline and you're going to move it 500 kilometers in a tanker truck, you don't use much of the energy content moving it from place to place, and that's why gasoline is so attractive. But look what happens to hydrogen. 100% of the energy content is consumed by taking it 500, so that's not a fuel. I mean, you have nothing left. It's a real issue, and it's not really being discussed in the way that it has to be discussed. These are problems that you can't overcome. So that means you can't move hydrogen, basically, and it means that if you're going to use it, it has to be done on site at the filling station. That's a whole other issue. And you can't get around these problems because they're fundamental. So, and there's another way to look at that. If you look at what goes on, say, in the US and also in Europe, a mid-sized filling station typically will sell 25 tons of fuel each day. That can be delivered by one 40-ton gasoline truck. It would take 21 hydrogen trucks to deliver the same amount of energy. So it's a huge issue. And the hydrogen economy is not going to happen overnight and may never happen because methanol economy, maybe, but hydrogen economy is a real problem. Here's the Honda fuel cell car. Okay, this is you can see it's a four-seater. It's a very sophisticated machine. This is based on, again, it's a hydrogen fuel cell system. So this is a platinum-loaded system. And in fact, it's a very nice car, but okay, here you even see the annual fuel cost if you're paying. It's about $5 a gallon, or I'm sorry, $5 a kilogram for hydrogen. I think the important thing here is the price tag. It's $1 million, and it's $1 million because there are a lot of expensive things in that fuel cell, and it's a very difficult thing to replace an internal combustion engine, in fact, with a fuel cell. Now, where could fuel cells go in cars where it might make sense? There's a lot of discussion about fuel cells being used for auxiliary power. And what that means is you have an internal combustion engine here, or it could be a hybrid, and then you use the fuel cell somewhere back in the trunk. This is actually being looked at by BMW and Chrysler Daimler. Small fuel cell that when you're idling would produce power for the air conditioning and power electronics in the car, navigation. That makes sense because when you're just sitting there, you consume a lot of energy. But that's probably not going to be a PEM. More than likely, that'll be a solid oxide fuel cell. Okay. There are other alternatives. If you look at the electric vehicle program, there was a lot of money spent on EVs. And EVs basically, those programs are gone. There are no EVs really. There's no EV economy either. But the information learned in the engineering of electric vehicles led to the development of hybrids. And here you see, this is the Toyota Prius, and in fact, probably many people know this, but the Toyota dealership in Berkeley is actually the #1 dealer in America for the Prius. And so these are being sold at it's Berkeley, so that's different too. But people are adopting these, and people seem to be pretty happy with the Prius. And it's $20,000. It's not $1 million. So this is real. This is real technology. And there are the new fuel-injected turbo diesels, which also do quite well, and the emissions are low. This also can deliver 50 miles per gallon. And diesel's coming on strong. And they're not very big in the US, but that's going to change. Okay. Now, what about stationary power? This is probably where we're going to have the biggest impact of fuel cells. And I think this is the most realistic market. So again, it's because you have this large advantage in efficiency. You can build a large fuel cell. You don't need platinum-loaded catalyst because we're going to use something that operates at a higher temperature and doesn't need platinum. All right. So here are your options for stationary power. There are companies trying to develop PEMs for stationary power. One of the problems is, okay, if you start with methane and and water, and you're going to steam reform that, well, that occurs at a fairly high temperature. And PEMs don't like CO. It poisons the platinum because they operate at low temperature. That means you need a shift reactor to remove the CO and operate the PEM at 80 C. So you're reforming at 750 C, and you're operating it at 80 C. Well, that's a huge efficiency loss. So in fact, these devices, these systems, don't really have no advantage over the grid in terms of efficiency. It doesn't make a lot of sense. If you look at an SOFC, though, high temperature fuel cell, here, in fact, the water comes from the exhaust, and you can see that it's directly fed, methane is directly fed into the SOFC, or molten carbonate fuel cell. That's solid oxide fuel cell. That's what SOFC means. It operates at the temperature range where reforming occurs, and these can be quite efficient. Efficiencies can be even as high as 70% if it's combined with a turbine. All right, what's the market for stationary power? In the US, the energy product exceeds $500 billion annually. So it's a big market. It's really big. And the global market's expanding very rapidly. And in some cases, that expansion is being supported by things like coal-fired plants, which can be very polluting. So we'd love to see this market expansion satisfied by non-polluting fuel cells. And where they'll fit is probably here. It's really the market for new power generation. You're not going to displace plants that are already amortized, already in place. But when countries are putting in new infrastructure, new power plants, that's probably where SOFCs can fit. And that's $17 billion a year, so it's huge. It's a very large market. All right, where do you buy one? Well, they're expensive still, and we'll discuss what the issues are in terms of this cost. So if you look at the developers of solid oxide fuel cell technology, and the developers are Siemens Westinghouse, used to be Westinghouse, it's now Siemens Westinghouse. Cummins, the diesel company, is doing it. Delphi is developing it for cars, for auxiliary power units. And there's a number of companies. General Electric is also involved, and they have a substantial program. But the problem is this. If you look at phosphoric acid fuel cell technology, okay, in 1999 it was $3,000, and it was fairly mature then. And it was discontinued at $3,000 a kilowatt. It's too expensive. And the reason it was discontinued is that they saw no way in which they could drop that cost. If you look at molten carbonate and solid oxide, they're currently at very high system costs. And this has to be $400 a kilowatt. And it's up around $10,000, $11,000 a kilowatt. So this is what's, and of course everybody projects small numbers for, 10 years from now it's going to be very, very cheap. And it's very easy to do that because 10 years is 10 years away. But the question is, how do you get from there to here? And actually you'd like to go lower than that, because then you can really compete, and that's what's going to cause this technology to get adopted, because ultimately it's the price of electricity that people care about. Even if it's green, people have to pay twice what they pay now for electricity, they won't do it. So the goal, SECA is a DOE program. The goal for the system is $400 a kilowatt, and it's $400 a kilowatt because that's what you buy diesel generators and gas turbine systems at. Okay. So what's a solid oxide fuel cell, and what are we doing about it at Lawrence Berkeley? Ultimately, it looks like, or fundamentally, it looks like this. You have, again, this is a ceramic membrane. So typically, we have a thick ceramic membrane which conducts oxide ions. And in fact, and you have a driving force across there, which is really the difference in PO2 across this membrane. So on one side, you have, again, you bring in methane. Here on the air side, you're actually producing water. You're consuming oxygen, producing water on this side, and that water reforms the methane to form hydrogen in situ. So the hydrogen, all this reforming happens in the SOFC. We don't need a separate reformer. So that's all great. Okay. But these kind of what we call thick film devices, this thickness of this plate was typically 200 microns. And because of the resistance of that plate, the temperature of operation was limited to 1,000 centigrade. And that's pretty high temperature. And at 1,000 C, if anything can happen at the interfaces, it will happen. So you have to really engineer these electrolyte interfaces well. Otherwise, you get degradation. And 1,000 C also means you can't use metals. Very difficult to use metals. But you'd like to use metals because metals are much easier to form and machine. Okay. So if you look at, now we get into a bit of the technology, if you look at the polarization or the losses in a device like this, electrochemical device, there's an IR term or an ohmic term, which is basically just the resistive drop across this membrane. And there's a charge transfer term, which is essentially what's happening at the electrodes, and it has to do with how fast that reaction occurs. And there's what we call a mass transfer term, which is how fast the gas goes through the electrode. At these temperatures, that's generally not a problem. So how do we get the temperature of this fuel cell down? If we start with something like this, with a thick electrolyte with thin electrodes, those are screen printed on, we can actually kind of reconfigure that. So now instead of having this thick ceramic plate, why don't we just have a very thin plate? It's a very simple idea, because in fact, if you do that, the resistance is just going to be directly proportional. So if we go from 20 or 200 microns to 10 microns, the resistive drop across here gets a lot lower. And in fact, we could run this thing at 800 centigrade now. And you can start to think about metals. And maybe we can go even lower. And so what happens when you do that? Well, the IR term gets better, and the electrode resistance decreases because this goes as a surface area. So the question really is, why wouldn't you do this? It makes so much more sense. Well, almost everybody is using this approach. And really, this original approach was started here at Lawrence Berkeley, and now it's been adopted by many, many companies and developers. Okay. How do you make that thin film? Well, making 10 to 20 microns of a ceramic, there's lots of things you could think of. I mean, the semiconductor industry knows how to do this. I mean, you can think about things like chemical vapor deposition or laser ablation. You could sputter, plasma spray. All these things will put down thin films. The problem is we want to build a fuel cell almost the way that people make coffee cups. I mean, just fire, some kind of like a clay. Because that's real cheap. These are not inexpensive techniques. It's okay if you're making a Pentium chip. It's not okay if you're making a fuel cell. So we decided that really all those things didn't make sense in terms of an ultimate device that could really be commercialized. So we developed a technique. It's very, in some sense, it took us a while to get there, but it's very simple. We call it colloidal deposition. And we can make all sorts of electroceramic films this way. And it goes like this. You start off with an electrode. Now, the electrode for an SOFC is typically nickel. So you start off with nickel oxide, because when it's in the hydrogen environment, it'll be reduced to nickel metal. So you start off with a very simple thing. You kind of press this, make a tube. You can do all sorts of things. Okay, and we actually give it a pre-fire to give it some strength. And then we this is just, in fact, it's hard to see, just with an artist brush, but it's basically like a paint spray. We spray down a thin film of zirconia. And that is then fired, and what you see here, that is actually an SOFC. And if we look in cross-section at this is actually a scanning electron micrograph, this is the zirconia film, and that is about 15 microns thick. And you can see it's perfectly dense, and it's sitting on top of a porous electrode. This is where the hydrogen comes in. And this is the air electrode. And this technique, it's scalable, it's inexpensive, and it's geometry independent. So you can see just at LBL alone, We can make squares, circles, plates, in fact, tubes. That's all great. So, and the performance of these devices is actually pretty stunning. So when we started testing these things, we saw very quickly that the performance was actually better at 800C than the performance of fuel cells operating at 1000C because they had very thick electrolytes. So if you see here at the very top here, this is, in fact, at the time we did it, it probably still is, a world record for peak power density. It's the highest power density anyone's ever seen for an SOFC. It's now been duplicated by a number of other labs, but of course we were the first. And you can see that, oh, excuse me, let me turn that off. My son loves to put odd ring sounds on my cell phone. Okay. In any case, you can see here from the current densities, these are really extraordinarily high current densities. If you're familiar with battery technology at all, typically you run batteries at a few milliamps per square centimeter. These are thousands of milliamps per square centimeter. There's a lot of mass going across this thing. So it's pretty stunning. And it's 800C. So it just doesn't want to stop. Hold on. I'm just going to have to turn it off. Give me a second. All right. Die. It's dying. Okay. Now, importantly, when we got to this point, we saw that we could get the power density, we could bring the temperature of the SOFC down. The question is, now what's going to drive the cost? Because ultimately, if we're going to transfer the technology from Lawrence Berkeley to a commercial developer, they have to actually make a real commercial product out of it. So we started looking at the costs of all the components that went into this new configuration where we have a thin film cell. Now, here's the original technology, what we call conventional technology, where you have this 200 micron thick plate, and you screen print on electrodes, and they used something called an interconnect. And what that is if you have a flashlight and you stack batteries, you're series connecting those batteries to build the voltage. And fuel cells are the same way. You have to series connect them to build up hundreds of volts because they run at about 0.7 volts apiece. So this is the interconnect. It was typically made from something called lanthanum chromite, which is a conductive ceramic. If you add the costs up, this is the dollars per kilowatt for just raw materials. And that's not too bad, because remember, the target cost is $400 a kilowatt. The problem is, these are actually flow channels. The hydrogen and the air have to come into this device and run across the electrodes. And to make a machined ceramic, it's very, very expensive. It's not like machining metal. It's actually quite expensive. And so this has largely been abandoned because of that cost. Now, here's the anode-supported cell. This is what we were doing here at LBL. Now we have a large anode and a very thin electrolyte. And then you can screen print this. Now you can use, instead of this ceramic, stainless steel, because the temperature is low enough to do that. This is not going to get severely corroded at these temperatures. And you can see the price here. That's $3 a kilowatt as opposed to 40, and it's just sheet metal, basically. So that's all great. The problem comes in here. This is nickel. This is nickel and zirconia, and they're very expensive. The raw material cost is very high. So now you've gone from this to here. Now, you don't have any expensive fabrication on the right side, but it's too expensive. It's going to be difficult to commercialize such a thing. Now, you could ask, like, why don't we make this thinner? It's because that's where the strength of the cell comes from. That plate has to be stacked and has to be sealed. And so if you go too thin here, it has no strength, and it'll break. And these things do break. Okay. So the target cost is $400 a kilowatt system. That means that the stack, because that's system, and the system has more than just these components. It has power electronics. It has what they call plumbing, things like that. That means that the stack really has to check in at less than $85 a kilowatt for anybody to really, truly commercialize this in a meaningful way. Okay. So there is the Westinghouse approach also, Siemens Westinghouse. That's a very large effort, by the way. And it's a very slick approach in that it's tubular. They make tubes. And tubes are nice because the seals are much easier. As opposed to these square plates, they have to be sealed on every edge. They have a seal on the end. And the way they do that is they start with a air electrode, and they do something called, it's CVD-EVD. It's a vapor deposition process. It's really expensive. It's a batch process, and it's tremendously expensive. And even this, what's called an interconnect, is put down by plasma spray. It's fine for thermal barrier coatings for turbines, but not, again, it's too expensive for fuel cells. So this approach becomes very expensive. It's also the most advanced. There are 200 kilowatt Siemens Westinghouse fuel cells that have been in continuous operation for 30,000 hours. Some of these tubes have survived 60,000 hours of testing. So it proves the technology, but they'll never get the cost out of this. Okay, so what are we doing here? A few years ago, Craig Jacobson and our group came up with a very unique idea, which was that to basically take this thickness of the nickel YSE and replace it with stainless steel, because most of that thickness was there for mechanical support. And it's kind of foolish to spend a lot of money on something that merely is kind of supporting the structure when you can use stainless steel. And it's not trivial how you build this thing, but if you look at the cost implications, now you have something, it's $40 a kilowatt, very inexpensive, but more importantly, it's very strong, because now instead of the structure being based on ceramic, it's based on stainless steel, which is very, very strong and very electronically conductive. And it will survive quite well at these temperatures. So this is the basic concept of where we're heading now. And so what we had to do then is go from this structure to something like this. And of course we did it because that's what you're seeing. So what it meant was replacing this zirconia film stays. I mean, that's there. So that's the 20 micron zirconia film, a little thicker. But now what we've done is this electrode, which was in fact millimeters thick, is now just a very small section of it, about another 20 microns, will get put in between the steel and the zirconia. And so the bulk of that mechanical support here is replaced now by stainless steel. And this is a very tough, very durable structure. I mean, you can literally hit this, you can hit these with a hammer, as opposed to this structure, which if you dropped it from a distance of a few feet would shatter. And it's a problem in terms of building fuel cell stacks. This is very tough. But anytime you go from a somewhat conventional system to a new system, you introduce new interfaces. There's an interface here that's new, and this interface is the same. But this interface is brand new, stainless to the electrode. And so there are bound to be some issues. And so that's largely where our research is focused. But if we look at the performance, this is now, for the first time, a steel-supported SOFC. And in fact, it's not 2 watts per square. So you can see here now we're at about 140 milliwatts per square centimeter. The current is less, so the performance is not as high. It's almost as high as it needs to be, though, for commercial fuel cells, because they're not going to run at these exceptional power densities. And at 900 C, you can see that these things are hitting 300 milliwatts per square, which is about where they tend to run. But still, the performance has to be elevated beyond this. Now, what about these steel structures? Is there already technology around that we can borrow from? In fact, it's really it's like a filter. It's like a stainless steel filter. And there are plenty of suppliers in the US and abroad of such structures. This is just a stainless steel tube, which is used for a filtration membrane. And you can see that the pores, this is in cross section, are actually exactly what we want for a solid oxide fuel cell. And so we are now working with these companies, Paul, another company, Amatec, that supplies stainless steel powders, and they're very excited about the possibility now of going from just simple filtration technology to energy delivery. All right, we have another approach in addition to what we call co-fired approach, and that's called post-fired bonding. Now the reason this is exciting is this would allow developers of fuel cells that already have in-house processing to adapt a new technology. In other words, many of these fuel cells developers do this. They start off with, as I mentioned, nickel YSE electrode, and they have a thin YSE film on top of that. That was really essentially developed at LBL. But this would be thick. Now we're going to say, why don't we take these components, make them quite thin, and we're going to reinforce it with steel. So we co-fire that structure, and we make this laminate you see here. And it's going to be fragile, so you're not going to be able to build a stack with it. So we're going to introduce strength by bringing in steel. And the steel can be like perforated steel, which is used in everything. It's ridiculously inexpensive. Or we could use just a porous stainless steel. Either one would work. And what we need to do then is just braze. We put a very thin layer of some kind of a braze on the steel and on the fuel cell. So we have a braze layer. We move that over. And now on both sides, we're going to introduce stainless with this braze and bond it to the cell. And that's what that thing looks like. And I'll show you in cross-section. So that now that is this structure now bonded to steel, and that is very, very strong, very conductive. And if you look in the edge view, there's your fuel cell now. So instead of a fragile ceramic device, you now have a porous stainless steel support on both anode and cathode. And you can make current collection easily by welding to either of these structures. And so you have fuel and air. And you can see that actually the thickness of these components is about 500 microns here, and for the whole cell here, and same here. And this structure that you're seeing here, this is the ceramic fuel cell. So if you expand that, that's what's in there. So now we have the solid oxide fuel cell encapsulated basically between steel supports. This is a very, very tough, strong structure, and it'll be very inexpensive and easy then to put into a stack and build SOFCs from. So this will meet all the cost targets we need to meet. The question is, what's the longevity of this structure? We don't know yet. We just started building these things. We're just starting to test them. But if it works, if there are other problems to solve, the advantage here is we're solving the right problems, because if we solve them, the materials used in such a structure can meet all the kind of market demands in terms of cost. And you end up with something you really could then put into distributed generation, home fuel cells. And we're working also with other companies to do precisely that. So in terms of fuel cells for the future then, yeah, I think it's just about right. If you look at some kind of a timeline, and these things are really hard to predict, phosphoric acid, PEM. Phosphoric acid has actually already been discontinued. The efficiencies weren't bad. I mean, they were getting up here upwards of close to 40% efficiency, but the cost was really too high. And PEM, I mean, there's a tremendous amount of PEM. When I say PEM, that's proton exchange membrane. It's the fuel cell that's going into the Honda fuel cell car. It's a fuel cell that Toshiba's talking about for laptops. It has some problems. Cost is, in terms of distributed generation, the cost is going to be a huge one. And you're never going to get the cost out of platinum. Platinum's platinum. It's certainly, you don't get any economics of scale. In fact, it'll go the other way. If there's a higher demand for platinum, it'll get more expensive because it's scarce. So that has, I think, a limited, others would probably argue with me, but I think there's a limited time span for that. And this is the solid oxide and molten carbonate fuel cells. They're both too expensive now. But there are no raw materials now in these systems that preclude commercialization. And so it's a question now of engineering and making sure that the people who are actually developing these things are not just building large demonstration units, but in fact keeping an eye toward the real market, which is to compete with gas turbines and diesels. And then ultimately, there's kind of these hybrid SOFCs. Here you get into very high efficiencies, and this is where you start combining fuel cells with gas turbines and use the fuel cell as kind of a pre-combustor for a turbine. And in fact, you can deliver energies in excess of 70%. There's very, very high system efficiencies there. And there's talk when you use cogeneration, use the waste heat of these 21st century SOFCs where you approach 80% system efficiency. That would be great, I mean, if we can do that. And there's reason to believe it's possible, but all of this is going to be really driven by cost, because again, it's the cost of electricity that in the final analysis has to be competitive. LBL, what do we fit? In these three boxes. So what we're developing here then could fit into all these systems. And of course, we're talking to and working with a number of developers on this. All right, I just want to thank the team, Craig Jacobson, Luke DeYoung, of course. We have a number of postdocs, Marisa Marrero-Cruz, Stefan, Igor Villarreal. He just left LBL. He, in fact, was visiting from Ikerlin. Ikerlin is a Spanish energy company. We're working with them to build a small solid oxide fuel cell for use actually in residences. So in Europe then, or at least in Spain, the idea is that you would have like a 3 to 5 kilowatt SOFC in your basement. It would produce both power and hot water. And the reason that there's an attractive market here is that people in Spain pay an energy price based on a limit. And so your rate is dependent on what the limit is. So you may pay for 10 kilowatts. Beyond that, governor goes off and you lose power, everything shuts off. It's a bit obnoxious in a way, but it allows them to manage the load. And so they would like people would like to have an SOFC in the basement so they could add to that and produce power above and beyond that. Keiji Yamahara, he's from Mitsubishi Chemical. He's working with us. Mitsubishi is interested in potentially being a supplier of materials into the SOFC market. Andy Lemming is a graduate student. Li-Ming Yang, Yuri, who's sitting here, I think, right there in the front, another graduate student, Xuan Chang, and then we have actually a large number of undergrads who have done a lot of the work in this program too, in addition to the graduate students. So we have a very nice team, and they've really made all of this possible. And of course, we have to thank the people who give us research dollars. And that is US DOE through the SECA program. This is this kind of next generation solid oxide fuel cell program. ICRLN, again, that's where Igor Villarreal comes from. Praxair, now Praxair is interested not in so much fuel cells, but oxygen separation. The same structures I described which allow us to generate energy also can be used as electrolyzers, and you can do oxygen separation. And in fact, the oxygen separation device will be a commercial product. And DARPA's funding, they love this kind of stuff. Little SOFCs that you can hide, and they can power little sensors and other things that we don't really know about. But it's an interesting program. So the SOFC in this case is going to be about this big, about a 5-cell stack, and it'll be about the size of a quarter. And in fact, that's also going quite well. And then MKS, and that's the secret. So MKS is they work with the semiconductor industry, and they provide also process gas for the semiconductor industry, and they are interested in what we do here largely because of what we did in oxygen separation. They have a different idea. But those are our funding agencies. And that's it. Yes.
How do you predict solid oxide fuel cells playing into the transportation industry?
There actually are a number of efforts right now looking at how you can factor that in. And there's some kind of pre-commercial efforts. Now, the idea, most people in SOFC do not envision taking an internal combustion engine and replacing it with a solid oxide fuel cell. The automotive market is tough in a number of ways. One is ICEs are so advanced. There's been so much money pumped into that technology, and they work very, very well and last a long time. So that's like the most difficult thing you could do. And also, it's so cost-driven. I mean, this target of $400 a kilowatt for power generation, it's a tenth of that for traction. So it's $40 to $50 a kilowatt. So even at this, with this approach, which is mostly stainless steel, very cheap, our raw materials costs aren't there either. So traction's really tough. But where they may fit, and in fact, where the development is right now, is for something called an auxiliary power unit. So you said Delphi has a large program with BMW, and what they do, they're building a fuel cell, in fact, have built one, that sits in the trunk of the car. And since it runs at high temperatures, you can actually bring gasoline right into it and reform it, feed it into this fuel cell, generate about 5 kilowatts of power. And the idea there is, again, it's a pollution issue. It's an emissions control. So you're in a car, you're in gridlock, you're sitting there, the engine essentially shuts off like a hybrid does. And then you generate power to drive the electronics and the air conditioning, and it's going to be very efficient. And that looks reasonable. And that APU will start off in luxury cars. I mean, you won't start it off in the kind of rank and file cars. But that has real possibilities. Cost will still, you still have to cost down, but it's nothing like the kind of cost concerns you have if you're actually trying to provide, motive power for the car. And so that's where they're going to fit.
Your critique of the hydrogen economy was rather damning.
Yeah.
And from my limited experience here at the laboratory, these huge government programs do not arise without a constituency that supports them. So I could either make the assumption that it was all politicians and no scientists that came up with the hydrogen economy, or that there must be some argument on the other side for why, even if hydrogen came free out of the ground, if I understood your presentation, you would still cost more to get it to the tank than it would. What's the argument on the other side? Why?
Well, you've got, it's a train that's been moving for a long time. You've got Ballard in Canada, which has billions in R&D money to develop PEMs. And you've got Plug Power and some of the other PEM companies that have raised a lot of money in the public market. Now, originally, the idea, because they didn't go after hydrogen at first for cars. The idea was you were going to reform gasoline in the car. You're going to have a reformer, you're going to bring in, so you're going to use liquid fuel, which made a lot of sense. And there was a lot of money spent on this technology, where you would have a gasoline reformer, it produces hydrogen, cleans up the CO, and then that hydrogen goes into the PEM. But that technology proved to be so complicated and so expensive that you had a number of developers saying, gee, if we only, because these fuel cells work very well with hydrogen, that's how everybody tests them in the lab. So if we only had hydrogen, then these cars would work. And now you could redirect those efforts and say, hey, it's not going to happen. You know, traction doesn't make sense. The trouble is when you're raising a lot of money in the public market, the market had better be huge. I mean, it's just an economic thing. So if Ballard needs $100 million or $200 million to continue development, they have to have a very large market they're going after, and that tends to be cars. Residential power is another possibility, and so this thing has taken on a life of its own. I think you're going to, now the other issue, which is a political one, is that there's a lot of money that's going to go into the hydrogen economy. And I'm sure there'll be some very good science that comes out of it. But the vision thing, I mean, does this make any sense in terms of, you know, reality? Can you really use hydrogen in cars? A lot of people aren't discussing it because you might get funding, you know, for hydrogen storage and other things. It's tricky. And I think, so the criticism's been a bit muted, but it's a huge issue. It really is. And one last thing is that, you know, the discussion typically in the scientific community about hydrogen storage typically revolves around storage on board. So they're not concerned so much of moving the hydrogen from a plant that makes it to a filling station, but even in the car, because the car has to carry the hydrogen. And you can do that either with a pressure vessel, which tends to be too heavy, or you can look at these kind of absorbents and metal hydride alloys and things like that. And that tends to be where the focus is in the scientific community. But there's this larger issue, which is, you know, how are you going to get the hydrogen from A to B? And then there's all this energy that has to go into producing it. Methanol makes a lot more sense. Liquid fuels make a lot more sense.
Are there any ecological concerns about hydrogen being leaked into the atmosphere from leaking compressed vessels?
Well, there's probably, I mean, there's a safety issue, again, with any kind of pressurized fuel. But I think that's probably not, I mean, there's already discussion of kind of training and infrastructure development for handling hydrogen. So I think that'll probably be taken care of, and it's not particularly toxic material. So that's probably not too much of an issue. I think the real issue is, you know, it's not really a fuel in a sense. I mean, it's not a fuel the way methanol and hydrogen, and gasoline are. So I think the safety concerns probably can be addressed. But certainly, if you have a high-pressure system with hydrogen on board and there's a leak, that's a bit of a scary thing. I mean, if your whole cabin fills up with it. So you need hydrogen sensors then. So you're going to have sensors that detect the presence of hydrogen on board. That's an issue.
Question about your comments here and there about the utilization of waste heat. That's in the Spanish program, they're thinking about that, and then
right.
At the top of your graph towards the end, you get these really high efficiencies. I'd like to know why you think that's actually a good thing, a good target, a good thing to think about, since you can get to the pretty close or at those efficiencies
right.
with internal combustion engines and microturbines if you capture the waste heat.
Right.
At obviously a much lower cost. I actually think that the target for the fuel cells is really going to be not using the waste heat, but very efficient conversion of fuel to electricity.
Right. I mean, that's largely true. The problem with, for instance, if you're going to envision using, having your own generator, you know, at your house, for instance, for no, it's hardly realistic to think about diesels and ICs just because of the noise. I mean, they're very loud, yeah? And maybe you could do some baffling, but most people don't want to have a generator running. I mean, even if you look at a simple thing, the reason Cummins is interested in the first place, their market is RVs. And the reason is, like, you go into a national park, most national parks have curfews because diesels are loud, and they don't want those things running. So Cummins, they sell to that market, but they realize that, in fact, if they can have an SOFC running quietly with low emissions, probably will have no restrictions on their use. And so there are these other advantages that will drive residential use.
To convert all these 132 million cars to hydrogen would require energy to produce that hydrogen that would be of the order of what is generated now. In other words, additional power plant if you are going to do electrolysis. If you are going to use hydrocarbons, you would still need the energy for reformation.
Right.
So
that's right.
you would not be solving
No,
energy problem. And the other question is on distributed power. If we're going to move the car to the workplace and then feed the energy into it, there is one thing. The smaller the electrical machinery is, the less efficient it is. It's an old truism of electrical engineering. Right. In other words, your losses would be greater than the transmission losses are now when you have huge generators who has very high efficiencies. So how this is a great research and has a lot of spin-off, but I do not think that the core question of energy freedom is coming from it.
No, there's two parts to this. You're starting the first part about the hydrogen economy. Yeah, I mean, obviously, I have to agree with you. I mean, no argument from me on that. I think there are some very basic problems that are going to be difficult to solve. In terms of distributed generation, I think there's still a lot of sense in looking at distributed generation. I mean, say 200, 400 kilowatt units. I mean, you do have transmission losses, certainly, and they can be pretty large. So I'm not sure I agree with you on the second point, but as you scale, there are other issues too, though. As you scale down to really small sizes, for instance, these small SOCs like in the 3 kilowatt range, 5 kilowatt range, you know, there's this whole issue of having that stuff on the grid, which is possibly a safety issue, and that still has to be addressed too. Because if you have a brownout and the grid goes down and you're going to send service people out to maintain the grid, and you have people, you know, kind of willy-nilly providing power back into, you have a live grid then. And so there are a whole bunch of infrastructure issues that still have to be addressed. So that's not all completely resolved. And so how this is kind of introduced is, I think, still in discussion and still has to be addressed.
I have two questions. Now, when you're reforming either gasoline or natural gas to get hydrogen, what happened to carbon form? You know, is it getting...
Oh, you're still making CO2. Yeah, you're not going to get rid of CO2 here. It's just going to be a question of, just a question of efficiency. So, I mean, in any of these fuel cell scenarios where you're forming, you know, you're going to have CO2 as a byproduct. So if the efficiency is high, you just consume less fuel, there will be less CO2 emissions, but you don't get rid of it.
Right, in assessment of sort of automotive market, you always talk about the efficiency of fuel cells. But as people look at the potential gains in efficiency for internal combustion engines or diesel engines, are there any great leap ahead of us?
With diesels and other
diesel
things?
or
I'm
ICE
sure there are. You know, I mean, this kind of improvement in diesel technology, which has happened over the past 10 years ago, has been pretty incredible, in fact. And the U.S. is actually, you know, lagging in terms of adoption of diesel technology, because I think everybody still thinks of diesels, you know, based on these buses that go by that are shooting out a tremendous amount of soot, but that's not the technology that's available now. So I think, yeah, I mean, that's a moving target, and so anytime you're developing a new technology, you have this lag issue, that you aim for something and say, well, this is competitive, and then assume that everything else is static. But yeah, 10 years down the road, everything else gets better. And so if you're not aiming, you know, significantly, you know, far beyond current technology, then you may have nothing in the end. And that's an issue with almost all technologies. And that's why you don't want that's the danger of these long development cycles. So if you say it's going to take 10 years to develop a fuel cell system, it's a bit scary that way, because you don't know what's going to happen in 10 years with the other technologies, and you know, when you're looking at multi-billion-dollar markets, they have a lot of R&D support that comes back in from all that revenue. Definitely an issue.
Excuse me, it's really loud. Is there any research being done or even any place in this technology for superconductivity?
Well, maybe, I mean, possibly in transmission, but not really within the SOFC technology itself, no. Yeah.
This harks back to an earlier question. Let's assume you're right about everything you've said. You probably like to assume that.
Yeah.
One can certainly make a case for non-transport stationary fuel cell.
Yes.
Technology.
Yeah. Right.
But the big money, very big money,
yeah,
is going into the hydrogen economy.
Yes, it is.
PEM fuel cells, transportation.
Right.
again, if you're right about what you've said,
Right.
why are we doing this?
Well, I mean, look at, you can look at the electric vehicle program. Look at EVs. A lot of money went into EVs. I mean, I don't know what the total tally is, but it's got to be at least $500 million. And GM made EV1, and Ford had EVs. They all had EVs. But, I mean, it's kind of a crazy thing, but if you sat down and just did a back-of-the-envelope calculation on the cost of even raw materials that would go into the batteries that would make an EV possible, you could see that you couldn't do it. You just couldn't do it. I mean, almost if you filled the case with sand, it was tough to do it. So why were they doing that? Well, the interesting thing is, in the final analysis, it made the hybrid electric vehicle possible, but not the EV. So you could see that, no, EV couldn't happen. It just, there are no batteries yet that are inexpensive enough to make an EV possible. It's just too expensive a proposition. But it really did. Now, I think if you look in Japan, they built EVs too. But the whole time they were building EVs, they were looking to hybrid electric vehicles because they thought they made a lot more sense. And so they had a parallel effort, a very serious effort, and they launched the hybrid electric vehicles far in advance of the US, which had a larger EV program. And so that's what can happen. I think you can get these spin-offs, but you still have to understand that, you know, the vision can't be that, oh, we're just, everything's going to get cheap magically, because it usually doesn't. And so the EVs died on the vine because of that. Now, it may be that years from now, and there are other battery chemistries being looked at, that we will have a battery chemistry that can go into a full EV, but it's not happening yet, and that chemistry is not here yet. And so it's certainly not the first time something like this has happened, where huge sums of money were spent, and many people were convinced that something was going to happen, and it didn't, you know, but something else did. And so I think that's the kind of thing that can happen here. We can have a lot of people working in fuel cells. You know, who's going to have, usually, you know, quite often it comes from an entrepreneur. Quite often the big companies have very large programs, and they just have a certain momentum, and then some small startup sees an application for a PEM fuel cell, an SOC that no one else has seen that makes sense, where it's maybe not so cost-driven at first, and they do something, and it blossoms from there. But it's hard to predict those things. But there are some, you know, basic issues here, particularly with the hydrogen economy, but also in terms of putting, you know, fuel cells in cars with replacing an internal combustion engine. There's a reason that the Honda fuel cell car is $1 million and the Toyota Prius is $20,000. And it's not just that it's the first one out, because they've been trying to do this for a long time.
How can nanotechnology be of any assistance with
well, I mean,
some of these
people are
problems?
certainly looking at nanotechnology in all these electrochemical systems, because, I mean, electrode reactions are almost always driven by surface area. So if you can get to finer and finer surface areas, you can get, you know, less or higher efficiencies and less polarization. So in the SOFC, these high temperature systems, it's a bit difficult because nanostructures probably won't survive the temperatures, you know, the coarsen and sinter. PEM is a nanostructure, really. I mean, this PEM technology, to get the platinum cost down as low as they can, they use essentially nanocarbon, which is decorated with platinum. And they drove the platinum cost down a lot in PEM. And so that has worked. That approach has worked in PEM. The trouble is now they're getting to the point where, you know, they almost have, you know, one hydrogen reaction per platinum atom. It's getting to that point, so you can't reduce that much more, and that's the issue. In SOFC, maybe. I mean, I think as we bring, the interesting thing is there's a window. It's kind of this magic never land of in the range of 300 to 400 C. Nobody's there yet. So SOFCs are up at 750, PEMs are at 80, 90 C, and that's why they need platinum. If you could get to this, you know, this other region, 300 to 400 C, where methanol could be used as a fuel and it's reformed easily at that temperature, get away from platinum, that would all be great. The trouble is, nobody has a solid membrane that works at that temperature, an ionic membrane. And also the issues of catalysis come up. So there may be some interesting work that gets done in that range, and then you could probably use things like nanostructures and nanoparticles, and that might be a very fruitful area to work in.
Thanks, Steve, again.